And the topics that I want to cover today are two. First, I want to discuss a little bit about harmonic oscillator. You know, stuff like phase space, quadratures, and Wigner functions. And then I want to look at some specific topics concerning Gaussian states and channels. So just some definitions and symplectic transformations. And several examples.
Graeme, you will have to scale it up a little bit.
Okay, thank you. I don't have. Yeah, I'm not a professional teacher like many people. I work at a company, and we don't often do this kind of thing. So I will scale it up.
This is okay. Whatever you do, max you scale it up.
Okay, okay. So we have symplectic transformations and some examples. So by the end of the day today, what I'd like to get to is an understanding of some interesting Gaussian quantum channels and states that we can look at to try to analyze the communication capacities of and various properties of, like distillable entanglement, private capacity, classical capacity, that kind of thing. And in the back of your mind, you should have, let me just put a box around this. In the back of your mind, you should have as an example EM waves, okay? And I'll talk about a single bosonic mode, and what I mean by that is we have some EM waves, and all the quantum numbers are fixed except for the degree of freedom, the number of photons that you have in that mode. So you should think of a Hamiltonian. Maybe there's some frequency associated with the mode that you're interested in, so I fix the frequency, and then the Hamiltonian is just p squared plus q squared. Where these p's and q's are the field quadratures. So if you took some class in electromagnetics, you know, usually what you do is you draw one of these. I think it's called a phasor diagram. So you have this phase space, you have p and q, and typically what happens with an electromagnetic wave is it sort of whips around in this circle like that. And these are just quantum operators that represent those sort of classical degrees of freedom. So you should think of, I fixed the frequency, I fixed the orthogonal angular momentum, etc. Okay. And in order to describe such a system quantum mechanically, we use these raising and lowering operators, which I can write in terms of the field quadratures. Okay, and these have just as a quick taking of the temperature. How many people probably know what the commutation relations are of this? Okay, good. So they have these commutation relations. A dagger is equal to the identity. I just will go through this quick and get us to the point where we look at more difficult things. P and Q commute like this. You can get this directly from these definitions. And the Hilbert space of this mode is described according to some discrete basis where n labels the photon number of the mode. And these A's and A daggers behave like this. Okay, and one way that we can rephrase this Hamiltonian over here is the Hamiltonian is just equal to h bar omega times a dagger a plus a half, and you recognize this as the number operator. So now, when we're dealing with an infinite dimensional system like that, actually it gets kind of annoying trying to write down the states. So we have to develop some tools to write down the states of these of a bosonic mode that we don't use in finite dimensional case. Okay, so I want to tell you about phase space representations. So first, what we do is we're going to collect these P's and Q's. I'm going to talk about now multiple modes. So I have now a finite number of different bosonic modes, and we want to know how do we describe the quantum state of such a system. So I'm going to let R just be a vector of these different quadratures. So I have Q1, P1, all the way up to Qn, Pn. Okay, and I'll make it the transpose of that, and I'm going to define this symplectic form as just the direct sum of a bunch of ones and zeros. Okay, so I could write it like this, or I could just put 0, 1, minus 1, 0, 0, 1, minus 1, 0, all the way down. So based on this commutation relations, this commutation relation, now we have that Rij, Rk commutator with Rl is just going to be Ijkl. And we'll define the displacement operator as e to the I xi times j times r. Okay, where this xi is some 2n-dimensional vector. And these guys satisfy the following relations when we multiply them. So there's some phase that I add plus the sum of these two arguments. Okay. So just in the interests of making sure I'm aiming this at the right way, have people seen this before? Some have, some haven't. Okay. Well, this is already sort of some of the properties of this displacement operators I think will be useful to go through in the tutorial session. So one thing you might be interested in, one property that's probably useful is, well, I'm calling it a displacement operator, but why? Well, the point is, if I take one of these quadratures R sub k, and I conjugate it by this guy, what I get back is R sub k plus did I write this correctly? Yes, good. R sub k plus some translation of R, okay? So these guys literally displace the value of the quadratures in phase space. And this is actually...
The previous two one probably would have put transpose on side because you have considered them as column vectors.
Oh, you're right.
The next one also.
Good. Thank you. And this actually, I can write it in another way, which is just that the commutator of this displacement with Rk is going to be proportional to the displacement. And these are a very useful set of operators. And actually, what we can do with them is use them to express the quantum state by using these guys as a basis for the state space. So I can write, maybe I will erase this guy over here, and I can write.
What is
This? Oh, this is just the commutator of this displacement with d is, did I write it wrong? No, is equal to d transpose this way. I just take this and multiply it by d on either side, right? And then you get it. Okay, and why do I mention these things? Well, I can use them as a basis for the state space. So rho I can write now as 2 pi to the n integral over all possible values of this psi of some function psi chi sub rho of psi times this guy, where this chi sub rho is called a characteristic function, and it's just given by trace of d psi of rho. So this is sort of a non-commutative Fourier transform that we use, and these guys are like kind of like the sines and cosines that you'd usually use as a basis for your state space. And this is called the characteristic function. And the Wigner function is just the Fourier transform of this characteristic function. The regular commutative Fourier transform. And it's a sort of quasi-probability distribution, meaning it's like a probability distribution, but it can go negative. Okay, so these objects are going to be sort of useful for us in describing bosonic systems, but specifically in describing Gaussian systems, or Gaussian bosonic systems. But before we do that, let's do a couple of examples. So actually, I'll state a property of this characteristic function and give a sort of sketch I'll just mention that it's true, and also in the tutorials probably I think it'll be useful to go through this. But the point is, if I take a derivative of this guy with respect to these psi's, you can think of what happens. These displacements just have some r's up here, so by taking a derivative with respect to psi, I bring one of the r's down, and then if I set psi equal to 0, the derivative of this thing at 0 is just going to be the expectation of one of the r's. And if I take a second derivative, I can get expectation of say, a product of different r's, if I like. So if I write this down, this derivative and I'll write it. I'll just write down what you do. J times r of rho trace. And similarly, if I take a second derivative, I can pull down 2 copies of r. And now what I want to talk about is what do I mean when I talk about a Gaussian system? Well, or a Gaussian state. That's just a state where when I learn the expectations of the first order moments and also the second order moments, that tells me everything I need to know about the state. And indeed, the characteristic function over here and the Wigner function are going to be Gaussian functions. So let's define the displacement vector of a state, any state. It's just going to be equal to trace the expectation of rho rk with respect to rho, and the covariance matrix is just going to be the expectation of of the second order moments shifted by the expectations of the first and symmetrized. Yes?
Which one should be RK? The derivative of the characteristic function.
Yeah. Well, this thing sub k.
I want to say psi equals 0.
Yes, there we go. Yeah. Okay, so now if we have displacements dk, or displacement vector d and a covariance matrix gamma, we end up with and the state and the covariant and the characteristic function is a Gaussian. We can actually express the characteristic function explicitly as chi sub rho of psi equals this. Okay, so this is what a Gaussian state is. It's just something whose characteristic function looks like that. And now I want to just talk about a couple of states that are Gaussian. Okay, so let's look at some examples. Well, the first example I want to look at is just the vacuum state. Okay, so this, it turns out, is a Gaussian state. So let's compute what the displacement and covariance matrix are. Okay, it's pretty straightforward. Right, the expectation of P, just by writing down this P as a sum of A's and A daggers, it's just going to be minus I over root 2. Where do we go? And that's going to be, let's see, this is going to be minus I over root 2 of 0a, 0 minus 0a dagger 0. And this actually is going to be 0, and also this is going to be 0. So both of these terms are 0. So the expectation of P in the vacuum is 0. Similarly for Q. But now we can calculate what the expectation of Q. Okay, so what this means is this displacement vector is equal to 0. Now we have to compute the covariance matrix. It's going to be, well, matrix. It's going to be a 2 by. We're going to have, based on this definition, 2 times the expectation of Q squared up here. We're going to have the expectation of PQ plus QP here. Same down here. And 2 times the expectation of P squared down here. So,
How do you connect the expectation value of P going to 0 to the displacement, with this displacement going to 0?
oh, I see. Because this d sub k is just the trace of r sub k with respect to rho, and remember, this r vector is just a vector of p and q. And this rho I just let be a projector onto 0. Then the trace turns it around, and that's what I have to calculate. Where did I go? Okay, so now we want to compute each of these 3 terms. These 2 are going to be the same. So we should just compute what q squared is. It's going to be equal to 0. We're going to just substitute in what q is. A plus a dagger, A plus a dagger. It turns out there's only really one term here that matters. That's going to be equal to a half 0, a dagger, 0, and this is just going to be equal to a half. And you get a similar answer for p squared. So now we have to compute these guys. And it turns out, well, first of all, I'm supposed to compute this expectation, but instead I'm just going to compute this one and add its complex conjugate, which is going to be expectation of QP. And that turns this into twice the real part of expectation of PQ. Okay, so what is that? Well, expectation of PQ, I can just substitute in again the definition, and it turns out it's just minus I over 2. And that means these off-diagonal terms are 0. So what I end up with this state, for this state, is just the identity. Okay, so that's the vacuum. There's another interesting example that I'll just throw over here, which is a coherent state. You just take these displacement operators and apply them to the vacuum. And let's ask what this displacement vector is. In this case, it's going to be the expectation of these r's with respect to this guy. But that's equal to, I'll put this dagger in to make sure everything works. That's going to be equal to this. The kth element of that is going to be equal to this. Which from the properties, this commutation relation with the displacement and the quadratures that we mentioned before is just going to give us this. Which in the end is just going to be this psi sub k. Okay, so by translating these vacuums around using these displacement operators, I end up with states that have displacement given by the parameter of the displacement operator. And actually, you can do a computation of what the gamma is, and it ends up being the same. So it's just a displaced vacuum. So now, I want to do a third example. We've been talking about pure state so far, but I want to talk about a mixed state, and a sort of mixed state that came up in Fernando's talk yesterday, thermal states. So I have a Hamiltonian associated with my system, right? It's just this guy. And a thermal state has some temperature associated with it, and it looks like this. So this, it turns out, is also a Gaussian state. And we can prove that, for example, the displacement of this guy is also 0. And the way to do that, or one way to do that, is you can basically expand this in the number basis. And if you write this in the number basis, it ends up looking like the following. And then you can use the fact that the expectation of PQ with respect to a number state is equal to just I. It's imaginary. And similarly to over here, we just need the real part of that. So these displacements end up being 0 for this thermal state. OK, yeah, sorry. I should have given you a relationship between n bar and beta, which I will do right now. It is, well, I think this is also a good calculation to go through in the tutorial. The displacement of this thing is 0. The covariance matrix is just going to be proportional to the identity with some nu. And nu is going to be given by 2 times e to the beta minus 1 inverse plus 1. And n bar is just going to be equal to, well, you can do it 2 ways. 1 over e beta minus 1 tells you what n bar is. Or if you want to do it in terms of beta, e to the minus beta is equal to n bar over n bar plus 1. It's the average value of this. Pardon? But oh, I'm going to take omega h bar to be just 1 the whole time now. I should, yeah. Right, otherwise this doesn't make any sense. Okay, so we should just say h bar omega. Okay, so this is also a Gaussian state. You can see it has, well, I've computed what this gamma and what the displacement are, and you perhaps will just have to trust me, or we can do a calculation later to show that actually the covariance matrix of this guy is also a Gaussian, so this is a Gaussian state. And it's going to turn out to be important to us. It's going to turn out to be important to us to figure out what exactly is the entropy of this thermal state. Yes? This should be beta. Let's make sure it works, okay? So.
What do you mean by covariance matrix of this state is Gaussian?
Oh, the covariance matrix is proportional to the identity, and I meant to say the characteristic function of the state is Gaussian, right? So every state is going to have a covariance matrix, but it turns out only for Gaussian states do the covariance matrix and the displacements tell us the entire state. So let's see if this is right, okay? So when beta is big, beta is inverse temperature. So when beta is small, rather, the temperature is high, okay? And when beta is small, this is small, so this is big, which means this is big, right? And if this is big, that means I have a very hot state. So it's the right way with this beta. Or put another way, the expected number of photons in your thermal state when beta is small should be large, right? Because when beta is small, it's hot, and that's consistent. So these guys, I think, are written in the right way. Okay, so let's compute what the entropy of this state is. Okay, so what's the entropy of a thermal state? Well, we have the state written over here. Let's just bring it over. And remember, the entropy of a state, rho, is equal to minus trace of rho log rho. Today we'll make it a natural log because things are more convenient that way. And we can rewrite this now in the number basis. So that's going to be equal to it's going to be equal to sum from n equals 0 to infinity. I'm going to put a minus sign. I have to put this probability. And then I have to take, I'm going to put this in front. And that's going to be equal to now the log of the probability. So it's going to be n plus 1 log n bar plus 1 minus n log n bar. And I think I put an extra minus sign in there. Right, so this is going to be equal to the entropy of now our thermal state. So we can now split this sum into two pieces, or we can carry out this sum explicitly, actually, through the following. This is going to be equal to, this depends on n, this depends on n, this doesn't, this does, this doesn't, right? So now what we get using the following, this just tells us that if I take these probabilities and average over the photon number, that the expected photon number is n bar. That's what I mentioned over here, that we didn't compute, but we can later. We can use this expectation together with this expression for the entropy to show that the entropy of this thermal state is equal to something called g of n bar, where this g function is just n bar plus 1 log n bar plus 1 minus n bar log n bar. Okay, so that tells us the entropy of a thermal state, and we've gone through some examples of Gaussian states. These are just states that are completely characterized by their displacement operator and their covariance matrix. So a question you might wonder is which covariance matrices and displacement operators are allowed.
Generally, you could have stated the condition on what covariance matrix should obey.
Yeah. So what should a covariance matrix obey? I'm going to show you something that a covariance matrix does. It turns out any covariance matrix obeys this property, and any matrix that obeys this property is a covariance matrix. I'm only going to show one direction. Maybe in the tutorials, Professor Simon can help us with the other direction. He's the guy whose paper I read about this topic in. And that's not the first time this lecture that we may have to ask him for some help, because he's done a lot of very interesting work and important work on exactly this topic. So let's say, well, one thing we got to know is not every covariance matrix is allowed. So we know that delta P delta Q by Heisenberg uncertainty has to be bigger than or equal to a half, right? And that tells us that the expectations of P squared and Q squared are also not going to be able to be both very, very small, right? Can't be both small. Okay, so let me give you. Well, first I just wanted to show you a matrix. Okay, I'll call it Aij. It's just trace of Ri rho Rj. Okay, this is not the symmetrized matrix. Okay, and I want to show a little claim. I claim that for any quantum state, this A is positive. And the proof goes like this. I take some vector v, or u rather, and I'm just going to look at u dagger a u. This is a complex vector, and I want to show that thing's always positive. So no matter what vector I sandwich this a between, I want to show the result is always positive. That.
Probably need an object dagger.
Hmm?
Probably need an object dagger.
Yeah, but they're Hermitian, right? So I'll just leave it. Yeah. But actually, so it's you're right. So this is just equal to sum over ij of ui bar trace ri rho rj uj. And this is equal to, I'm just going to take the sum inside the trace, trace of sum over I, ui bar, ri, rho, sum over j, uj, rj. And that's going to be equal to just trace of r tilde dagger, r tilde, where now in order to make that clear, I do have to put the dagger in, of rho. But now what I have is a positive matrix, right? Explicitly it's Hermitian, or sorry, this is explicitly positive because I take r and r dagger and multiply them together. So this thing has to be positive. Okay, so we've figured out that A is bigger than or equal to 0. And this actually tells us the constraint that we need on the covariance matrix, because if I look at the entries in A, Aij is equal to, I can write it as the average of the anti-commutator of Ri and Rj, the expectation of that, and the commutator of Ri and Rj. But the commutator of Ri and Rj is given by the commutation relations we know. So this is just equal to half of gamma ij plus identity times j sub ij. Sorry, square root of minus 1 times jij. Okay, so we know that this matrix is positive semi-definite. So we also know that I'll write it up here, that this gamma plus ij should be positive semi-definite. And actually, this thing here is Hermitian, which means it has real eigenvalues, which means also gamma minus, this is equivalent to gamma minus ij should be positive semi-definite. And yes? Sure. Well, the first thing I should warn you is I've implicitly assumed here by accident that the displacement is 0. Okay? Now, we can assume this, and then what we'll do is, or we can either assume this and show the result this way, or you could just replace Ri with Ri minus di, and Rj with Rj minus dj. We'll just leave it like this. So the goal is to show this, that for any covariance matrix, gamma plus ij is positive semi-definite. And the method is by taking this aij that we can show is positive semi-definite, and then explicitly writing it in terms of gamma ij and the commutator of rij, which is just this j. And I realize I probably should have used indices k and l now, because j sub ij sounds kind of strange. Okay, so we define this a sub ij as just the expectation of, with respect to rho of ri, rj. And we want to show that this thing is positive semi-definite. So what we do in order to show it's positive semi-definite is show that for any vector, when I compute this thing, the expectation of of a with respect to these u's, that the result is positive. That's what.
So unlike the r vectors, u vector is a c number vector.
Yes. Yeah. The u's are just complex vectors. They're not operators. Okay, so the way we show that is here. We compute this inner product of A times U and U dagger by writing it out explicitly here. Here I've taken this sum over I and j inside the trace. And I've taken the dagger, or the Hermitian conjugate of Ri, which I'm allowed to do because these things are Hermitian. But now we observe that this is the same quantity as this, with the exception of the extra dagger. Okay, so I use the cyclic property here and move, I guess this should have been R tilde dagger. I move this over to there. But now whenever I have an operator of this form, it's going to be positive semi-definite. So when I take the expectation of it with respect to this state, it's also positive semi-definite. Or it's also positive, rather, or non-negative. So now we know that this A is positive semi-definite, but now we can rewrite this A in terms of gamma ij and j. Just because I can always write the product of Ri, Rj as the average of the anti-commutator of A and the commutator of A. Does that? Okay, great. Okay, so this is the sort of key property that we need our covariance matrices to satisfy. And any such covariance matrix and displacement operator is going to have a Gaussian state associated with it. So now I want to talk about what are the operations that we're allowed to do. What are the physical operations that we can do that preserve this property of Gaussianity? Okay, so I want to talk now about symplectic matrices. And symplectic matrix will tell us a way, given an allowed covariance matrix, to generate new allowed covariance matrices. Okay, so first let me just define what a symplectic matrix is. I'll call S symplectic if it leaves this J matrix, the symplectic form, invariant under conjugation like this. So Sj, S transpose is equal to J. Oh, sorry, yeah. S definitely has to be real. S is 2n by 2n dimensional, and it's real. It doesn't have to be symmetric, right? Good. And with such an S, we can always associate a unitary S, or a unitary sub S, that acts on these, acts on the quadratures as just multiplication by this S matrix. So Rk under conjugation by this use of S gets mapped to the sum over L of SKL R sub L. And we'll call these Rk prime. And the purpose of this constraint on the symplectic matrix is just that these new Rk primes also satisfy the canonical commutation relations that the original R's did. And when we apply this unitary on the quantum state associated with a displacement d, what it does is it maps that displacement to S times d. And the covariance matrix gets mapped to S gamma S transpose. So now we have to just check for our own sanity that this new covariance matrix is actually allowed. Right? We had this property that we wanted to make sure we satisfied. Okay, so let's say we start with gamma. We know that gamma plus ij is positive semi-definite.
Excuse me, I have a feeling that should be S and K rather than K. If you want US prime US to be equal essentially to S prime S, I think then this is.
I trust your judgment on that. It's
I don't want people to get confused.
yeah.
Yeah, even if you also insist that US prime should correspond to SS prime,
I said that.
then you have no choice in this matter.
Okay.
At this stage, you have a choice, but if you insist that US times US prime should correspond to
S.
S times S prime, then you have no choice.
Okay. Well, I would like to do the multiplication in the normal way. So I'm going to rewrite it in this fashion. Okay, so now we know that this is positive semi-definite, right? That means it has eigenvalues that are all positive, or non-negative at least. And because of that, if I take some matrix and multiply it, or multiply it like this, these guys are real, remember, so this is the same as the dagger. I've just changed the basis, but I haven't changed the eigenvalues. So this thing's also going to be positive semi-definite. But I can write that fact as just the new covariance matrix plus SJS transpose. That's going to be positive semi-definite, which is not a nice sanity check, which is just that the new covariance matrix I got also satisfies this property of physicality. It's just a nice sanity check. So this is still a physical state.
May I make one more comment?
Yes, please.
People should ask, why do we expect to find a unitary operator U of S which has that kind of effect? Why should there be a unitary? The reason for that is that R prime K defined by the symplectic transformation obey the same commutation relation. And then there is a von Neumann theorem that commutation relations, standard commutation relations have up to equivalence only one irreversible representation.
Okay.
So one should know, we know in advance there should be operators U of S. That's
Okay.
the reason for their existence.
Okay. Thank you. It's well, I don't know how many people have given a talk in a room with people who know a lot more about the topic than you do.
All the time.
Well, I'm glad they're nice, right? Because it could be scary otherwise. Okay, so now let me give you some examples of some symplectic transformations that are useful to us. Are there, by the way, before we go on, are there any questions at this point? Yes.
I'm a bit confused about the US RK US dagger. So US is a unitary matrix which is I'm a bit confused about
Okay. So remember, these RKs are observables on this Hilbert space spanned by the photon numbers, right? So it's infinite dimensional. And now, you remember, you can either do the Schrodinger picture or the Heisenberg picture. And in the Heisenberg picture, when you do an operation, you conjugate your observables by some unitary, right? So this is just a mapping of these old observables, R sub k, to a new set of observables, R sub k prime, that's associated with this, this symplectic operation. So these R sub k primes are just given by what happens when you sum up these original canonical variables using this symplectic matrix. And this is just a representation. You know, this is the kind of operation that's going to happen on the level of just the observables here, this mapping from R to R prime. And this is just an expression of, as we were just discussing, if there's a mapping from one set of observables to the next that preserves the commutation relations, the canonical commutation relations, then there's some unitary that allows them, that allows you to implement it. So I'm just saying, with each symplectic operation, there is some unitary that does this.
Graeme, if you will permit,
Yes.
a statement which will act as a translation between what you said and
Okay.
what she will better understand. See, these U's are operators in the Hilbert space. Even for one mode, it's an infinite dimensional Hilbert space. Now, Graeme is considering n modes, so it's a tensor product of n infinite dimensional Hilbert spaces. So U is an infinite dimensional operator. Now, what that gives you is a isomorphism, well, almost an isomorphism, because I don't want to jump on me. Almost an isomorphism between that object and the S matrices, which are 2n by 2n matrices. So it is this that makes the whole thing very amenable and almost driving to some complete answers.
Okay, thanks.
It's used only for Gaussian situation.
Pardon? It's
Only for Gaussian
Oh, yeah, sure.
It is complete answer.
right. Okay, so now let's look at some symplectic matrices that we haven't looked at before. So I'm going to let A be a real number. And I want to look at this matrix. I just want to check this thing's symplectic. It's called a squeezing matrix, or squeezer. And you see what it's going to do over here is it's going to take one of the modes and multiply it by A, and the other and divide it by A. Okay? So it's going to sort of, if you think of this picture in phase space, the Wigner function, which was the covariance or the Fourier transform of the original characteristic function, if I apply this to say, if I apply this to a vacuum state, which has a Wigner function that looks like that, like sort of a circle, it's going to get mapped to something that looks like that instead. It's going to get squeezed out in one direction and in the other direction. So let's just check that this is symplectic. What we have to do is take the matrix and multiply it by, or conjugate this symplectic form with this symplectic matrix. The transpose here is the same, so we're in business. And then this is just equal to 0a minus 1 over a 0 times a 0, 0, 1 over a, which is just equal to the original thing again, right? Because this 0, 1, minus 1, 0. The vacuum state over this way a bit. Okay, so now we can sort of play with this a little bit and see what it does. So we have some condition on when these covariance matrices are going to be physical. This has to be true. So now I want to just use these symplectic operations. We know that these map physical covariance matrices to physical covariance matrices. So I want to ask a simple question, which is, when is a diagonal covariance matrix physical? So there are two things I could do. I could either write down this with this original gamma, but I want to save myself a little time, so I'm going to conjugate this gamma to something else whose physicality is equivalent to the physicality of this using this symplectic matrix. So if I let A just be square root of D over C, and then I conjugate this gamma by SA, I end up mapping this guy this covariance matrix to this one, now something proportional to the identity, and I can save myself some time in computing eigenvalues. So, for example, I take this covariance matrix. I want to know when it's physical. So I can write it down like this: plus identity ij. This is just going to be equal to root CD I minus I root CD. And then the characteristic equation for this matrix is just going to be root CD minus lambda squared minus 1 should be equal to 0. And that means lambda plus or minus of this thing, right? So the two eigenvalues of that thing are just going to be square root of CD and plus or minus 1. And I want those to be both positive to make sure that I satisfy this constraint. So you see that for any diagonal covariance matrix like this, we're going to need that the product of CD should be bigger than or equal to 1. So this vacuum state that I gave you sort of minimally satisfies this physicality condition. And thermal states, which have C and D equal to each other but strictly larger than 1, are not going to saturate this. They're going to be sort of, they're going to be sort of strictly positive and not be at the edge. If I take a vacuum state and then I squeeze it like this, again, we're going to be just barely satisfying this inequality. Now I want to state a theorem that is very useful, but I don't think we'll prove, that I'm not going to prove today. Maybe we can discuss it during the tutorials again. But it's a very important theorem. Again, going back to members of the audience, that tells me if I have some covariance matrix, gamma plus, that's physical, so gamma plus ij is positive. And we have some oh, please.
Lambda plus minus should be greater than or equal to 0.
Oh, yeah. You're right. And then that gives us the CD should be positive, or bigger than 1. Okay, so the thing is, it's not always easy to just look at some covariance matrix and figure out what is going on with it, right? So you want to make sure it's physical, so you can check this. And the theorem that I want to state is, let's suppose I have a physical covariance matrix. Then there's always a symplectic matrix. So there's a sort of transformation to some normal modes, basically, such that this gamma, when transposed by these symplectic matrices, takes a block diagonal form. And this is just a 2 by 2 matrix. So what does that mean? That means I have some gamma that describes some large number of modes. If I do a symplectic transformation, it's just like a redefinition of those modes into some other canonical variables, and I can always find some transformation from the original gamma into some very nice looking form where I have the new gamma is going to be just a direct sum of things proportional to the identity, which, as we saw before, these are just thermal states. So that means any Gaussian state gamma up to unitary I can think of as a tensor product of thermal states on non-interacting bosonic modes. So all of the action in, let's say I'm doing some sort of, trying to understand some bipartite Gaussian state, all of the sort of action is going to be in this symplectic operation. It's going to be in, what kind of non-local mapping from this product of thermal states do I have that gives me some sort of interesting entanglement or interesting correlation properties. And I'm going to tell you sort of very little about the proof. It involves, going through something called a Williamson normal form, which tells me that any antisymmetric matrix, it's kind of similar. I can always write as a direct sum of small 2x2 antisymmetric matrices using some orthogonal transformation. These are called the symplectic eigenvalues of this gamma. And
You squeezed your letters.
Hmm?
You squeezed your letters. Sorry.
small again? Are they? Oh, sorry. But yeah, I could. Okay. I'll bring it up again. And you know, as I said, I'm not going to show you the proof. It's not because it's too long or something. It's because I don't completely understand it. Maybe we can have some help from the experts at tutorial. I do know that it's related to the symplectic eigenvalues are related to the eigenvalues of the absolute value of this ij gamma. And the point here is any Gaussian state is just unitarily equivalent to some thermal state. And that lets us compute the entropies for any Gaussian state. Because remember, entropies of a state also don't change under unitary transformations. So basically the way you want to, if you want to compute the entropy of some Gaussian state, what you do is you can figure out what this gamma is. You figure out what the symplectic eigenvalues are by doing this transformation, and you use that formula that we came up with earlier for thermal states. And there's a related property of these symplectic operations that I want to mention that also we're not going to prove, but it's just if I take some symplectic transformation, I can always decompose it as a product of three other symplectic matrices, two of which are orthogonal. And the third, the one in the middle, is diagonal, and it's just one of these squeezers. Yeah, so if you do the singular value decomposition, you get this, but then you have to fiddle a little bit because you need to make sure this is symplectic and this is symplectic. Right.
The score is orthogonal.
It should be orthogonal and symplectic.
So that should be SO. But doesn't SO2n belong to SP2n?
No, because think about, let's see.
Okay.
Okay.
But this is not SO.
Oh, you're right. Yeah. So as long as it's
Determinant should be 1, I think.
yeah, as long as it has determinant 1, I think we're okay.
What was the question? Belong to the mean subset.
Yeah, SO2n is a subset of SP2n. Is that true? No. For n equal to 1, yes, but not.
Only for n equal to 1.
I'm trying to think of an example. Do you have a quick example?
Well, SO, the intersection between SO2n and SP2nr is precisely un.
Oh, okay. You just take the real and the imaginary parts of the unitary. Okay.
Precisely un, and which is equal, which is as big as SO2n only when n equal to 1.
Oh, right.
That is a much smaller one. It's not missing by a few things. I mean, the number of parameters is very small.
Okay. Yeah. All right. So maybe we should discuss this.
Otherwise, every phase-space rotation is not a canonical rotation.
Right. Okay.
I mean, well, you said you wanted a quick example, but
Yeah.
now you take two modes.
Mm-hmm.
And if you do rotation only in the position coordinates Q1 and Q2 and do nothing to momentum, it is still a rotation in phase space, but it's not a canonical.
Yeah. There you go. Okay. So there's.
It's not it's an element of SO4, but it's not an element of SP.
Right. So actually, there are just tons and tons of them.
Yeah.
So Because we have all these extra constraints of maintaining the canonical commutation relations. Okay, so there. So proving this involves, well, something like singular value decomposition, but you have to make sure these guys and these guys are both also symplectic. And then the point of this is that tells this sort of.
In this case, what happens is if you do singular value decomposition, it's a property of the symplectic group that if you take a symplectic group element and do singular value decomposition, these factors automatically become a SO, and rather than not only SO, but it's a elements of UN. It automatically becomes.
It's automatic.
Yeah, it automatically.
Oh.
You don't have to do anything.
Well,
And you don't have any freedom to do anything about that. It automatically comes.
but does the proof automatically come?
Huh?
Is the proof automatic?
No, proof is also automatic. This is all in our classical optics paper.
Okay.
This all has been there. Probably 30 years old work with person.
Okay.
But I should add, there is a more recent paper by Simon Chaturvedi and Srinivas,
Uh-huh.
which gives all such results in very simple, very efficient way. Which year is it?
It was probably 90, mid-90s, maybe 90s or 90s. No, I think not all results.
Many results.
Not many results. I think it gives probably only one result. Yeah, but that's not he's not interested in the Lorentz group. I think.
I might be.
No, maybe I will tell you what.
But
It's a very good paper for young people.
okay.
I think this the Williamson thing that you are talking about.
Okay.
Now that see the Williamson took quadratic Hamiltonians and asked what are the canonical forms under symplectic transformation. I think there are innumerable number of canonical forms, not just one or two. Then we found that if the given matrix is positively definite, the coefficient matrix is positively definite, then the canonical form is diagonal.
Ah, okay.
So this is something that we picked from Williamson's work, which I think is we consider that to be one of the greatest achievements of our life. That we found that this piece was there in the Williamson's whole range of canonical transform. Arnold's mathematical methods book gives the Williamson's result as appendix 6.
Okay.
Even then, it's not easy to figure out that this result is sitting there. So, people to say that Williamson's theorem and give reference to Williamson. So, I know how many people have read the Williamson's paper. In this literature, in the quantum information literature, I know precisely how many people have read Williamson's paper. Because if they had tried to read Williamson's paper, then they would have gone and read the paper that Professor Munda was mentioning. That is a paper I wrote with Chaturvedi and Srinivasa. It gives a very simple proof of not Williamson's result, only this particular case that is relevant for.
So
that is there in Journal of Mathematical Physics. Maybe I will show you.
I would appreciate it. I did an awful lot of Googling fairly recently to get proofs of this.
No,
And
I think the mistake I did in my 2000 paper, I did not give this as a reference.
okay.
So part of the mistake is mine. I did two mistakes in the 2000 paper. One is did not give a reference to the Chaturvedi paper. Second one is I called this criterion as Perez-Horodic criterion.
Okay. Good. We have some time. But can we please can we discuss this theorem in the tutorial maybe, and we'll see what.
Yeah. Maybe some of these things, yeah.
Okay. So now I want to give just a couple of examples and then write down the channels that I'm going to be interested in for the rest of the week, or some of the channels. Okay. Okay, so now I want to give an example of a two-mode state. We've had some examples of one-mode states. I'll give an example of a two-mode state. It's called a two-mode squeezed state. It's a pure state. So first I want to tell you what I mean when I write this. So it's just a unitary on two modes. So I have P1, Q1, P2, Q2. And it's going to be like the action of a beam splitter with let's say, transmissivity lambda. So I'll just show you in terms of the symplectic transformation what's actually going to happen. And I may get off by a bit of a phase or something like that. So it's proof I'm not well. This. I'll just write it out first, OK? OK, so let me just make sure that I get the sort of end cases right. So if this is lambda equal to 0, so if there's no transmission, I expect that P1, Q1, P2, Q2. Fine? Oh, sorry, can you? Yes, sorry, there's a plus sign. So if you wanted to describe the way an actual beam splitter works, I think there's some fiddling with where the minus signs go. But as long as you have two minus signs and you check that in symplectic, it's OK. And this is a particular symplectic operation. And now I can show you using this transformation how to prepare an interesting pure state. I'm just going to do these squeezing operations. So now if you think this is squeezing sort of along one axis, axis like that, and this is squeezing along the other. And then I'm going to take a beam splitter with transmissivity 1/2 and mix them together. So if you think about what you expect to happen, you expect to have in this mode some circular state, sort of big thermal state actually. In this mode, there's some big thermal state, but in the two modes, you have some pure entangled state. So the covariance matrix that you end up getting is this. Okay, and the relationship between C and A we can compute in the two.
Are there some minus signs somewhere?
Yeah, some minus signs here and here. So this is called a two-mode squeezed state, and the point is it's sort of like the Gaussian analog sort of
The minus set, at least I'm not able to see where the other people are able to see.
Okay, here and here. Okay. Yeah, this is c squared minus 1 square root. Sorry. Okay, and the relationship between A and C we can also discuss later. The point is when you do lots and lots of squeezing, you end up with a state in phase space here that looks like this, and then here it looks like that. But then when I mix them together, they both look. And when I mix them together and just look at this fixed mode, Here I get something that looks like that. Here I get something that looks like that. But when I measure one quadrature here, it tells me about the different quadrature here. Oh, the same quadrature rather here. So this brings me actually to an important example of a Gaussian quantum channel, and that's just a partial trace. Okay? So what's a Gaussian channel? A Gaussian channel is just something that maps Gaussian states to Gaussian states. And in this case, the Gaussian state that I have in mind is this big guy. It's a pure state, actually. And by doing a partial trace, I can map it to some mixed state because the thing is entangled. And the way you do a partial trace with these covariance matrices is you just take a subblock. So this is the partial trace on, say, if that's the A and that's the B system. Partial trace on A is just pick out the subblock associated with that those covariances. Sorry, with those quadratures. So since I'm talking about Gaussian channels, which map Gaussian states to Gaussian states, I can describe them in terms of their mappings on covariance matrices, from covariance matrices to covariance matrices. That's right, it need not. Right? For example, in this partial trace, right? And if it's going to be lossy, typically it's not going to preserve them. However, if I have some Gaussian channel, I can always describe it in a reversible way as taking the original input, some vacuum states, which have covariance matrix 1, applying some symplectic transformation, some S, which I'm going to write out in a block form. And then doing a partial trace. So this I'm just drawing a garbage can, because that's how I think of tracing things out. You throw it away in the trash. Okay, so now this is a mapping from this input to this output, and the output covariance matrix just looks like this. And in fact, if you have any Gaussian quantum channel, it's going to act like this. It's going to map gamma to x, gamma x transpose, plus some y. Y is going to be positive semi-definite. And there's a condition on these x's and y's for being a physical or completely positive trace-preserving map. They're related to the condition that this matrix here be symplectic. Actually, what we require is y plus I times j minus x, j x transpose. That should be positive semi-definite. Okay, and another thing, candidate to check in tutorial is show this from the fact that we want such things up here to be symplectic. Oh, yes. Okay. Let's see. Oh, so I have some covariance matrix, and what I do is I append some pure state, some vacuum. I do some symplectic transformation, and then I trace out some portion of the variables. Now, the simplest case is if this input is the same size as that output, but it need not be. I can always just pick more or even fewer modes to trace out, and that will give me a different channel. So the most general form of a channel is going to be add some stuff, do a symplectic transformation, pick some things to throw away, and what remains is this. And actually, any transformation that looks like that maps gamma to gamma conjugated by some x, plus some y. If this y and x pair satisfy this inequality, will give me a physical, completely positive trace preserving map, and will be associated with some symplectic transformation.
So if I look at that and the corner one,
Uh-huh.
then y plus I times j minus something doesn't look like ZZ dagger. The coefficient of I is j minus x,
Yep.
jxt, doesn't look like ZZ dagger.
No, the y is going to be like ZZ dagger.
It's the y which is there.
Yeah. Right. See, this and that are exactly the same, except I took Z dagger. And this, basically, we're going to be able to get from taking this map and then making a two-mode squeezed state. You make a two-mode squeezed state. Yeah. So we'll make a two-mode squeezed state. We'll apply this channel to one of the modes of the two-mode squeezed state. Actually, if it's a one-mode channel, we'll do that. If it's multi-mode, we'll make multiple two-mode squeezed states. That'll give you some bigger state that's kind of like a Choi matrix. Then you'll insist that that state satisfy this property. And the physicality of that state will then be equivalent to this condition. Okay, so now I want to tell you a few examples. I think we have.
Probably it may be helpful to write the input-output relation for the single mode channel that you have described there. See, this is an action on the covariance matrix.
Mm-hmm.
But the single mode Gaussian channel will act on non-Gaussian states also.
Oh, yeah.
The action on the characteristic function level itself, if you give, probably that will be helpful to the.
Oh, okay. So roughly, you can think of this. This is how you're right. This is how the channel acts on Gaussian states, but it's going to act on it's going to be able to act on non-Gaussian states too. And roughly, what you get is a convolution of a Gaussian with the original characteristic function to give you the new characteristic function of the output state. Now, I can't, off the top of my head.
I heard something. See, for example, if like chi is your, I don't know what you denote as characteristic function. Right?
Chi, yeah.
Yeah, so chi of psi going to chi of x psi plus x times exponential chi of psi going to chi of x psi times exponential minus psi transpose y psi.
Okay. This is the mapping. Right. So that's actually simpler than what I was thinking. I was thinking maybe what it does to the Wigner functions. Then is it a convolution? Okay. So.
But this is now true for all states.
Yeah. So this is yeah. You're right. So if I have rho in, this is what rho out is going to be mapped to. So now let's look at a few examples. And we'll talk more about these examples tomorrow. So the first example is an attenuation channel. You just take gamma. It interacts with some vacuum state via a beam splitter. And what happens is gamma gets mapped to 1 minus lambda gamma plus lambda times identity. So what we have here is x equals square root of 1 minus lambda times identity, and y equals lambda times identity. So this is a good sort of model of what happens if I have some, say, optical fiber. I put a signal in, it gets attenuated by the channel, and I don't do anything further. Some of the signal just gets eaten. Another example that we'll look at is an amplifier.
So would lambda be an attenuation constant?
Yes. Now if you look at oh, do you want? Okay. Another thing you could think of is an amplifier. It maps lambda to, gamma to some g times gamma with g bigger than or equal to 1. Now, ideally, if you have some amplifier, you just want to amplify this gamma to some bigger signal. But the trouble is you have to add noise too to make sure the operation stays physical. So what you end up adding is g minus 1 times gamma. So another example. So again here, what we have is x is square root of g identity, and that should be identity, sorry. And y is equal to g minus 1 times identity. Now in both of those cases, these channels just barely satisfy this physicality. So that people typically call this a quantum limited amplifier because it adds as little noise as possible in the form of this sort of mixture with a thermal state, or as little noise as possible, consistent with the requirement that you get a gain of g.
1 and 2 really look like similar.
Yeah, they're very right. So basically, if I just said
one is gain, one is loss.
Right.
yeah, so I might if I put some absolute values in there somewhere, then I could write them in exactly the same way. But they actually do behave. Well, physically, they're quite different, right? This is a very passive channel. You just have attenuation. Here, there's something going on inside. We'll see it tomorrow. That's very active. You have to do squeezing in order to get this gain. So it's not a passive channel.
0 sum lambda plus g is 1. Loss plus gain is 1. So 0 sum gain. So lambda is equal to g minus 1 will do that.
I think that's only mathematics. Physically, these are very different objects.
Right. There's no sense in which you can subtract a covariance matrix, though. It doesn't really mean that much. So you do have to consider these two separately. So something that's kind of like this. Imagine instead of mixing with a vacuum, I have some thermal state here. I can do that too. I can just take gamma and some thermal state and ring those off a beam splitter. That gives me some trash here and some output of 1 minus lambda gamma plus lambda times this. And this is parameterized by two parameters now, a level of attenuation and an average photon number of the thermal state. And the fourth example I just want to mention is basically a limiting case of this. It takes gamma and maps it to gamma plus mu times identity. This is called a classical noise channel. And what do I want to say about that? Oh, this just happens in the limit of letting lambda go to 0 here, while you let lambda times c stay constant at mu here. So, and it corresponds, if you go over here, to just having a bunch of basically taking the input state on the Hilbert space and displacing it by some Gaussian distributed random variable. So that's why it's called a classical noise channel. It just displaces the input state by some Gaussian distributed variable. And one more thing I should mention is this thermal state, this thermal channel here, I can always write as, and one of the reasons it's important is I can always write it as an attenuation channel followed by an amplification channel, where the gain and the initial level of attenuation are sort of a function of these two parameters, lambda and the sort of average photon number quantity that tells you how hot your thermal state is. So you can think of these thermal channels, and indeed even these classical noise channels, as being derived from an attenuator followed by an amplifier.
Basically, you're saying that thermal business is coming about because of some kind of noise.
Yeah, and it could come from the noise inherent in the amplification you try to use in your communications. And with that, I think I'll stop, and we can talk. We have several things to discuss in tutorial, and also I think tomorrow we'll start looking at these channels in more detail. Thanks.